Okay. So I thought I'd talk a little bit about some issues in hardware design for Smalltalk. And I've been, since 1999, I set up a company to design Smalltalk processors. And I thought I'd talk a little bit about the history. It depends on what your interests are. I can go in several different directions depending on what you guys want to hear, what you already know. I don't want to keep repeating what everybody is tired of hearing. But I thought I'd start out talking a little bit about the idea that there are some processors are language neutral. That means they're not designed for any specific programming language. That's a thing that I've heard a lot. And then I'll talk a little bit about historical Smalltalk processors. But I probably wouldn't be the best person to talk about them. Some of the people that actually worked on them are here. And I could mention some details about some of the processors that I've developed over these 10 years. Most of them just got to the paper design. Some of them we actually had partial implementations and simulation. So depends on whether you're interested in that kind of detail or you prefer to talk a little bit about the history. I think that the history is really interesting. I love to study old processors, PDP-11s and all that kind of stuff.
SOAR.
Mentioned that. So
Sorry to shout. I couldn't resist.
Actually, usually when people hear about my project, they say, well, you probably don't know this, but there's some guys that designed a computer specially for a language, probably Lisp or something like that, and it was a really huge failure. So why are you doing this? You're making a really stupid mistake. And then what I tell them is, well, the reason I don't design a language neutral processor is that I don't know how. All of the processors that I've ever encountered are specific for some language. This is an awkward angle. I'm not going to get the arrow there. This is going to be very hard. So normally they will say, oh, well, there's the PC. The Intel processor, the 8086, that's not designed for any specific language. And I said, that's not the history that I remember. The processor was designed to run Pascal or assembly language. Actually a mix of it. You write the main program in Pascal and you'd have your modules. You divide your code into 64 kilobyte segments, and then some stuff, the string movement stuff would be in assembly language. It'd be a library that you'd call. And what I remember is that this wasn't a very good processor for running C. If you wanted to run some code that you're bringing over from the PDP-11, that's only 64 kilobytes or 128 kilobytes, that would work fine. But if you're trying to port SPICE over from the VAX, then you'd find that you couldn't. You'd have to rewrite the whole program. So the language, you had something that looked almost exactly like C, but you had the near pointers, the far pointers, you had the tiny memory module. You had the humongous memory module. And so the program had to be rewritten. So there was a certain focus here. And it was great because that's the language that mattered at the time. Pascal was the king of the hill. This is going to be... The problem is that the LCD doesn't show the image, so... Oops. Skipped a step here. So the previous...
Takes a minute.
The previous processor was the 286. It was an improvement. And then the focus has shifted to modular 2, or ADA, I don't know how to pronounce that. And Intel was facing competition from the National processor. It was the 16016 and the 32016. And the Motorola, the 68020, added a lot of instructions for modular programming. That was the focus of the day. We wanted to do modular programming. So you had all kinds of instructions, enter module, leave module, task gates, and stuff like that. And all this was added to the 286. And so actually then they found out that people weren't going in that direction. And the 68030 actually dropped the special instructions for modular programming. So if you had used that, you'd find that the next generation processor, your programs didn't run anymore. Intel has never done that. They always keep full compatibility with everything that's come before. Right? And the 386 was a really interesting transformation from that all that stuff that I showed previously. This was optimized for C and Unix. They kept everything that was before, but now the segments were 4 gigabytes instead of 64 kilobytes. So you could take all your applications that you had been running on your VAX and you'd compile it, a simple recompile, and it worked perfectly. And since they kept all the backwards compatibility, all that hardware task scheduling and stuff like that, that's what got Linus Torvalds interested in this processor. And the early Linux operating system actually did that. It used that kind of stuff. And they lost all this special 386 stuff when they ported to the Alpha processor. So most people who came later to Linux didn't realize that it was optimized for this particular processor. So this is an example. If I take any other example, if I take RISC processors, if I take well, actually there aren't many processors left other than the 386 and the Intel mainframe. But you can always see that there's one language or a group of languages that is privileged, and the design is optimized for that. So if that's the case, then my favorite language is Smalltalk. I don't feel guilty about optimizing for that instead of for C, or for Pascal, or for modular. Right? And here's some other processors that were optimized for Smalltalk. Well, the Recursive, it's a British processor. They actually had their own language called Lingo, but you could run Smalltalk on it. These two, the Swamp and the Sword 32, actually implemented the Smalltalk bytecodes we're familiar with in hardware. And let me start with the ones where Smalltalk was originally designed. I won't go really quickly through this. The Auto computer, it was micro instruction sets that was defined for it, was the Smalltalk bytecodes. Okay. Often, the Dorado was considered the ideal Smalltalk computer. It was very large, fast as possible. It was so loud and noisy and had so much heat that people would normally install it in the other room, and you'd run some cables and you'd have just a terminal in your room. And that was considered the ideal processor. This is actually a commercial one. That Dandelion was sold as the Xerox Star. And it's actually all the same architecture. And the idea was that the hardware was as flexible as possible, as programmable as possible. And a lot of experimentation was done. These were very interesting machines, and the Lisp machines were actually inspired by these. They were MIT's versions.
Were designed not just to run Smalltalk, but they were compromised to run Mesa, Lisp, and Smalltalk.
Yes, the most popular instruction set was the Mesa one. And these were actually the Lisp machines that Xerox sold also. but you could optimize for Smalltalk by loading the instruction set. The Dorado, for example, let me just go back. It could run 4 different instruction sets at the same time, and for every instruction it could switch between them. So it wasn't even when you're using it just for Smalltalk, it wasn't a pure Smalltalk machine. Normally your Smalltalk implementation was implemented partially in microcode and then partially in some other language. For example, you could have all the primitives, they were normally written in Mesa and then translated into assembly language, Nova assembly language. So, okay. So let's talk about the sorting. Don't have many details here. I'll just David could talk about it. What was interesting was the 3rd RISC processor at Berkeley, right?
Let me just say Dave Patterson was the faculty advisor.
Yes.
His name.
I should have put in.
Yeah, I just want to be sure he got his credit.
And he was also responsible for bringing Smalltalk to Berkeley, if I understood correctly.
Yeah, I brought Smalltalk to Berkeley. Yeah, I wrote Berkeley Smalltalk.
So here there was a student project where it had many of the same features as the RISC-2, the register windows, and what was unique was the tags, where every instruction you could see the data as just raw 32 bits, or you could have there was a tag scheme where the top bit would tell you if it's an integer or not, and if it wasn't, if it was a pointer, then some more bits would tell you what generation that the object belonged to. And for every instruction there was a bit that selected if you were using the tagged version or the untagged version. And to me the most interesting thing was all the work that they did measuring stuff, measuring the results and seeing what worked, what didn't work. And that was a major influence.
Best optimization right up the
Yeah, well, one of the interesting things was that it didn't have bytecodes. The sources were all compiled to machine language, and then they looked at the work that was being done at Xerox and the dynamic compilation stuff, and so a lot of this exists to this day in the Spark architecture, the Spark processors. Okay, so here's the mushroom. Okay, the mushroom, it started out as with the idea of being a bytecode machine, and then when they saw the SOAR, if I understood correctly, when they saw the results that the SOAR group had obtained, then it looked a lot more like the Spark.
If I may, you may be amused to know that back at Berkeley, I was the first one to do a Smalltalk with 32-bit direct pointers and no object table. And now for this work, I'm putting the object table back in.
Right.
I mean, you have to get back in.
That's a whole other story.
And there were a lot of interesting features. They had some, they used some FPGAs so that they could experiment with variations of stuff. And one of the interesting things was that they had the data cache in such a way that they did have the object table, but it didn't cost them anything on regular memory accesses, only when the cache missed and they had to go to the main memory. Then they would have to look up in the table, and they had a tree-based table, so that it was the virtual memory for the machine. And This is a feature that I think that Mario still works on today, and it's something that hasn't caught on, but I think that it's was a fabulous result that they got, and they had the virtual machine. And another interesting thing is that the generations, the very first, the youngest objects, they lived exclusively in the cache. They never went over the system bus to the main memory until they lived long enough. So the first level of garbage collection occurred inside the cache. And they got some very interesting results.
This work was so cool, we hired Mario to come join the Self project. It's just cool.
Yeah.
I'm glad to see you mentioning it. It's just cool work.
I've never heard of this machine. I'm embarrassed to say.
Yeah, and they actually closed it. It ran there for, I think, something like 10 years or more. They had a party where they shut it down. And one interesting thing was that as a side effect, there were several interesting side effects of this project. And one was that they collected all the cool Smalltalk software that they could find. And they had the first library, I think that before the University of Illinois, not sure, but the Manchester archive was the first collection that I was aware of cool Smalltalk stuff made available to the public. And what's interesting is that you have all these old projects, but there are ideas that still haven't been explored commercially. You can still learn from them. Speaking of learning, this is one that's really worth learning from. The Jelly Bean machine was developed at MIT. Now most of this group is now at Stanford, but back then it was this shows a board with 64 processors. Each processor, the original idea was to fit the processor's memory inside the same chip. And then they felt that the technology wasn't up to the task at the time. So there's actually 3 little memory chips, DRAM chips, implemented next to each processor. Here you can see 64 of them. And each one is connected to the 4 neighbors and also to a connector, so that when you stack together the boards, oops, there's something here. When you stack together the boards, you'll connect to the equivalent neighbor on each side, on each board. So here's a Sun workstation, it's the I/O processor, and here's the machine with 1,024 nodes. And they had a Smalltalk, they called it concurrent Smalltalk. The syntax was Lisp. It wasn't the Smalltalk syntax we're familiar with, but the semantics certainly was Smalltalk. And they had very interesting features. Sending a message was really efficient. It was you just wrote to a special register, and that word was already flowing through the network. And receiving it was also efficient. If a processor wasn't doing anything, and then the first words that arrived from the network started up the method associated with that. And they tried various alternatives, and they tried other languages besides Smalltalk. And they published a lot of evaluations, so anybody interested in looking at what kind of numbers you can obtain, what worked, what didn't work so well, it's all available on the web, so that you can figure out. And one thing that they did that I really liked, they had what they call the concurrent aggregates, where if you have an array and you declare an array with 10,000 elements, it'd be split up among the 1,000 processors and 10 elements inside each one. And to each processor, that array would look like a local object, because it had separation of local objects and remote objects, stuff like that. And this concurrent array, it would look like a local object. And when you sent a message to it, all of the 10,000 little pieces would coordinate. And so you wrote very normal looking sequential code, and it wasn't sequential, it was really parallel. So I think that what Dave showed here has a lot to do with what they were doing here.
Yeah.
Well, there are several other projects. Here I just mentioned the Smalltalk related ones, so there are also a lot of efforts to write Java processors. Sun had the Pico Java, there's the JOP, Java oriented processor. And there were other object-oriented hardware implementations, like the Zoom. I'm not going to mention them all. But I had started implementing Smalltalk machines in 1984, and I was using the Motorola 68,000 processors. And then I also did a design using the ARM processor in 1988. And in 90, I had gone back to school, and I got a scholarship to design an object-oriented processor. So I did a survey of a lot of material that's now easily available. I couldn't find it back then, but I was working on that, and that's when the Self group first started publishing results, and then they showed that their various optimization, they were getting negative clock cycles for sending messages. You know, they send a message and -2 clock cycles. Then said, how can you do that? Because they weren't interpreting everything that the source said. They were optimizing things away. And then when you divided the results by what the source said, that how many messages you had to send, they were sending a negative 2 clock cycles. And then I said, how am I going to do that in hardware? And so the design sort of shifted to an adapted Spark processor. But that project was killed as not academic enough. My advisor, he was in a sabbatical, and when he came back, he said, "Oh, the Spark is a commercial processor. Let's do something academic." So we used the 68020. Okay, so let me. Here's some. I tried several different directions. By 1999, the year 2000, FPGA started becoming large enough, and it started to become cheap enough that I could start designing my own processors, and I didn't have to keep working with commercial processors. Here's the one that I first designed. It's a very crude representation. The purple stuff is the external memory. It was 700 kilobytes of external cache, 64-bit wide, and it was a synchronous memory. So running at 100 megahertz, it gave you a new data every clock cycle. But it was pipelined, so you had to give it the address 3 cycles before. And when it did give me the data, I interpreted it as 4 16-bit instructions, where each instruction is a move instruction. This is something that several groups have researched called move processor. It's a bit simpler than the RISC processor. A single RISC instruction becomes 3 move instructions. You move register 1 to the A input of the adder, you move the register 2 to the B input of the adder, and then you move the output of the adder to the register 3. But on average, every typical RISC program will become 2 moves per RISC instruction. And then if your compiler is smart, you can start getting almost just one move per RISC instruction, because you can reuse the results from previous instructions. You do what we call software pipelining, and you send them directly to the results. And so on each clock cycle, I got 4 moves. These are buses. And the instructions were basically just addressing bits. And here are the units, right? So the idea was that in main memory, I had the byte codes. And then every time I had a cache miss, the compiler would translate these byte codes into these moves. But it actually was a great idea. And there are some other interesting features in this processor, but I won't go into it. I'll just mention that I'd need a really large compiler team to get this to work well, because it's really hard to find 4 interesting things to do on each clock cycle. A good compiler would leave most of these as knobs, and so all the hardware was going to be wasted. One interesting thing about this is that I actually was able to split this design into 4 FPGAs. But soon after, in 2001, the prices for FPGAs really came down, and the amount of memory inside the FPGAs grew. So I didn't have to have this huge external memory as the cache. It became easier for me to have 4 simpler processors, each one running its own thread, because then I can generate code for 1 move at a time, a simple instruction. So I switched to an architecture where I would have multiple simpler processors running bytecodes directly, and each one with its own local cache, more or less the architecture. Let me see here. Oops. Okay. This is no description of the Plurion processor. This is, oops. There. Okay, I'll just get 2 pictures. Here's, whoa, what's this? Stopped. Sticky keys, cancel please. Doesn't go up or down. Okay. Oh, yeah. I see now. This machine doesn't have page up, page down.
Talk about doing moves. We didn't talk about doing anything else.
What? The moves? Oh, yes. The move instruction was 16 bits wide. You had 4 of them in 64 bits. 3 bits told you the condition. There were 8 possible conditions. Always true, always false, if on 0, on stuff like that. And then you'd have 7 bits for the destination and 6 bits for the origin. And some of these destinations and origins were registers, regular registers. Some were the memory interface, so you could send it to the memory address and then the memory data bus. And a lot of them were functional units like adders, subtractors, and stuff like that. So everything happened as a side effect of moving to certain. One of the most interesting hardware things that I had was I won't go into it now, but the compiler, it used what we call the polymorphic inline cache, and there was a unit for that. There was a PIC unit, and it could branch to 3 different destinations in a single clock cycle. They could look at bits, and that was used by the compiler. So it was a mixed compiler. Here's the larger one. Okay, so here the Plurion, we had ring networks. This is something that I'm still using in my designs. Ring networks work better than buses inside large machines like this. And I had I/O processors for talking to the pins, to the external stuff. Later I eliminated these I/O processors and used the stack processor. I expanded the stack processor a bit so that I could use do both the Smalltalk stuff and the low-level I/O stuff. So this is machine, and I really need a page down key here.
It's probably the function key and up and down.
Yeah, no doubt. Exactly it.
It's just only 10 inches.
Okay. Now here's the interesting stuff. The interesting stuff is that there were the stack processor had 3 levels of stack. First, it was a really tiny stack. It's only 8 elements wide, although if you overflowed it, it could expand. It could use neighboring frames for expansion. So all the instructions would push the data to the stack and retrieve the data from the stack. And the second level is you had always one frame that's called the current one, but you could open additional ones. And then some of the data, instead of going to the current stack, would go to the open one. And this allowed you to compile Smalltalk from left to right. So when you were going to, you're evaluating an expression, and inside it you have a sub-expression, you'd open a new frame for that sub-expression. Then when the data was ready for it, it would already go into the right place. And then eventually you could, you had a third level here where you send a message, and then you get an entirely new set of current and open frames. So it was a kind of a strange thing, but the idea was that I wanted all of the data to, the moment it's calculated, to go to the right place, where it will go eventually, instead of being like the normal Smalltalk implementations where you have the context and then when you send the message, you copy stuff from the sender context to the called context and then back. There are other ways to do that. That's what Elliot is working on in COG. And I adopted similar situations. Let's just show the instruction set here. So basically, I had a prefix instruction that would add some bits to the following instruction. And then we had several kinds of jumps and send messages. And there were, for example, the literal. You could have the literal, it will push in the current frame, or the open literal, and that would create a new open frame, and then the first element of that new frame would be the literal. And you had the var and the indirect and the temporary. And so it actually was a very simple instruction set. Here are the extensions. These are called the special sends, and these are implemented in hardware. So add, subtract, and, nor, all that kind of stuff. But this is the heart of the design. And what's interesting is that each one of these was actually implemented as a different hardware module. So when I said, oh, I'm sending a message to this hardware, that's actually what I was doing. I was posting some wires, and then the hardware was doing the stuff that I wanted it to do. So this is the design that I started working on starting in 2000. And let me show a different one. Okay. This was a 16-bit design. This one I already talked about in OOPSLA 2003, so I'm not going to repeat it too much, but I'll go down there. And this is its instruction set. you also have a prefix to extend. And you have the special A, special B instructions are instructions that get their data from the stack. And then you have the jumps and send. It's more or less the same instruction set. But what is interesting is that since this was to be very low-level hardware, although I'm programming it in Smalltalk, and then let me show the special instructions. Okay, so here I have the test, clear, set, and toggle instructions. These 4 instructions make it really compact for you to do I/O to toggle the bits directly. And another set of 4 instructions that were interesting. We had these indirect instructions where probably a bit lower down. Where is it? Well, there are the instructions for you to access stuff inside an array pointed to by the stack, and that's used to implement efficient blocks, shared data between contexts. That's something that Elliot Miranda is working. He added to Squeak in the past few months, and I had it in this processor too. Just can't find it. And related instructions were these 4, where a stack word pointed to an array. It was a 4-word array, which had an object, an index, a step, and a limit. And so it implemented the next put, add end, and rewind instructions. And so it's sort of a hardware implementation of streams. So if you had 2 arrays, and you wanted to add them together and then put the result in a 3rd array, that's normally very awkward with just the basic instructions, because there's a lot of stack manipulation and stuff like that. With these instructions, it's practically a 4-instruction loop for you to do the jump. So it was good for streams, and it was good for low-level I/O. So that's the kind of stuff you can do when you design the hardware and the software together. That's a bit more complicated to do when either one is predefined. And here's a different instruction set. I'm not going to go too much about it. That's what I was working on for the past 2 years. And it was a RISC processor. It's sort of like the SOAR. I was compiling the source directly to the machine language, but I optimized the machine language so that most instructions took only 2 bytes, 16 bits. And most instructions did what normally you take 2-byte codes to do. So on average, this code was almost as compact as bytecodes, not quite. And well, this is the basic instruction set. You had the math instructions, and then the math with the literal operand, and the shift instructions, logic instructions, and then the store, load. There are a lot of interesting features in this processor, but currently I stopped working on this because so there's a group working. Let me go back there.
Did you do any simulations to compare how fast this would go at a given clock speed compared with stock architecture?
Yes, this processor would run about 100 megahertz on an FPGA. So
That's not what I was asking.
compare.
So if you actually produce this as a as a real chip, as opposed to simulating on an FPGA, and you could run this at 10 gigahertz.
Right.
How fast would it run Smalltalk compared to, you know, x86 running at a gigahertz?
I don't have detailed simulations, but my estimate was about, in the Squeak benchmarks, it probably run as many byte codes per second as megahertz. So if you're running at 700 megahertz, you'd probably run 700 byte codes per second, million byte codes per second. But where it really outperformed the common processors were in the send-receive benchmarks. That's what it was really optimized for. But I didn't get far enough to give you a good answer. Okay. 2 months ago, there's this group called Morfel. There's Merrick from Holland, and he's working with the Hawthorne Institute. It's a research lab in California. And they're trying to build supercomputers running Squeak images seaside. And they also want to build low-cost computers, the stuff that I was interested in. But they weren't very interested in this RISC-42 that I was doing, which had a corresponding Smalltalk. It was called New Smalltalk, based on prototypes. I also like prototypes.
Hey.
But they said, well, we already have all this Squeak code. Can we put in an intermediate step there where we would run Squeak? And I said, well, that's something that I've looked into about 3 years ago. And I think that it's possible to do a good design. It won't be as effective as something, a new design, but I agree that there's great value in running stuff that people already have. So there's this new SiliconSqueak. I don't know if the site is already on the air, but I'll just mention some details here. And well, here's Squeak running on the normal hardware. And this is the VM compiled to C and translated in machine code for whatever processor I have here. And here I have the image with lots of interesting objects. And there are 4 objects that I want to mention. There's this huge array which has itself a Squeak image. And this is detailed in the Back to the Future paper that introduced Squeak, so if anybody's interested in more details. But let's say that this red object is a bytecode interpreter. Actually, it's just one object, but to make it simpler, I show it as 3 different objects. Let's say that the blue one is the memory manager, and this is the primitives. Okay, so I split the virtual machine as if it were 3 different objects, and here they're running as normal Squeak objects. And then I have translated them from the reduced Smalltalk slang to C, and then I've compiled them, so here they are again. This is what's running everything that's on top of it. And well, there's a slowdown for each level, so all of these objects are running, this is running, let's say, 10 times slower than this one. Actually, sometimes it can be as slow as 70 times slower. And this, of course, run even slower because you have 2 levels of bytecode interpretation here. So what I said was, what if I had some magic magic piece of hardware that I replaced this. Let me open one. Okay, so there I have a magic piece of hardware here, and what it does, it makes, this is. It makes bytecode objects run as fast as native objects. Okay? So I'm using my imagination here, supposing. Right? So now this guy is running as fast as this guy. And if that's true, then these guys are running as fast as these guys originally were. Now these guys are faster too. If everybody here is faster, these are faster too. And now this is usable because it's running as fast as the Squeak I originally had. So that's great. And then I can even ignore these guys, these two guys, and use these guys since they're now fast enough. Okay, so there's a trick with that. So now, what if I can extend this? If I could somehow extend this to replace even this bytecode interpreter, since I have this magic hardware that runs bytecode so fast, now suddenly these guys are actually running as fast as these guys, which is faster than my original Squeak. So let's say that we're talking about a RISC processor running at 100 megahertz, right? And now I'm suddenly running everything faster. I'm running, on my first step, then I had my Squeak running as fast as it used to run directly on the compiled virtual machine, and now it's running actually faster than that. So that's the proposal for SiliconSqueak. And I actually have some information about this design, and the idea is to be able to run an average of 2 clock cycles per bytecode.